Section: Introduction. In this section, we explore how human language serves as a simplified representation of a complex and often probabilistic understanding of the world. Language models capture some of this complexity through token embeddings, where similar tokens are represented closely in a high-dimensional space. We ask whether we can leverage our understanding of the continuous nature of the world to enhance language models. For instance, we recognize that the word emerald is more closely related to shamrock than to pine when discussing shades of green. As large language models, LLMs, have become versatile tools for various tasks, the need for continuous representations is increasingly important. These models can benefit from understanding continuous values for tasks like arithmetic, decision-making, and forecasting. We approach the challenge of integrating this continuity into LLMs through probability density estimation. To simplify our analysis, we use a standard framework focused on predicting the next token, where we can discretize continuous values into bins. LLMs typically use a linear layer to project tokens into probabilities, allowing for flexible approximations of probability distributions, but they often ignore the continuous relationships between tokens. In contrast, a parameterized distribution approach, like Gaussian mixtures, can incorporate continuous structures but may oversimplify complex distributions. We propose the Fourier head, inspired by Fourier series, which are known for their ability to approximate functions. The Fourier head learns a continuous probability density function and provides a discrete approximation. This method helps the model better capture low-frequency patterns in the data while avoiding overfitting to noise. The Fourier head takes input values, learns coefficients for a Fourier series, and divides the range into equal bins. It then evaluates the learned density at these bin centers and outputs the probabilities as a categorical distribution. Our contributions include revealing the balance between the expressive power of the Fourier head and the smoothness of its predictions. We demonstrate that increasing the number of Fourier coefficients allows for modeling more complex distributions but may also lead to fitting noise. We also present a practical implementation of the Fourier head for sequential prediction tasks, enhancing its ability to model complex distributions. We suggest strategies for improving performance, such as regularization and careful selection of Fourier frequencies. Our results show that the Fourier head significantly improves performance in two large-scale tasks, including a reinforcement learning agent for an Atari game and a time series forecasting model, outperforming existing methods. Section Summary. In this section, we explore how to enhance large language models, LLMs, by incorporating continuous structures into their token embeddings through a novel, Fourier head, that learns a continuous probability density function. This approach allows us to better model complex, multimodal distributions, leading to significant performance improvements in tasks like reinforcement learning and time series forecasting. Section: Fourier head, definition. In this section, we propose a new approach to replace the standard linear layer used for token classification, which we call the Fourier series classification head, or simply the Fourier head. This head takes any vector as input and produces a categorical distribution as output. To summarize its function, the Fourier head processes the input vector, extracts coefficients for a Fourier series over the interval from -1 to 1, divides this interval into equal parts, evaluates the learned Fourier probability density function, PDF, at the center of these parts, and then returns the likelihoods as a categorical distribution. We will formally define this process in an algorithm and demonstrate its application in a low-dimensional example later. To illustrate the Fourier head's design, we replace a linear classification head in the audio spectrogram transformer for the task of classifying beats per minute, BPM, in audio samples ranging from 50 to 210 BPM. Although this task is relatively simple, it serves to highlight the design choices available when using the Fourier head. We group the BPMs into contiguous bins and utilize the Fourier head for classification, as these bins have a natural continuous structure where the Fourier head excels. We anticipate that the distribution of possible BPMs for a given audio clip will be unimodal, requiring only a few frequencies for approximation. In fact, our best model for this task uses just one frequency. We initialize the audio spectrogram transformer with pre-trained weights and train two models, one with a standard linear classification head and another with the Fourier head. The Fourier head significantly outperforms the linear head, achieving an improvement of 118% in the F1 score, which we attribute to the continuity bias of the Fourier head. We will present a graph comparing the learned probability distributions from both heads on the same input sample, showing that the Fourier head produces smoother distributions. Next, we discuss key considerations for using the Fourier head during training. The Fourier head takes a signal as input and extracts an intermediate representation of a probability distribution defined over a specific range. We optimize the parameters of this distribution by discretizing it and using cross-entropy loss for training. While the Fourier layer can also be trained directly on continuous values, we choose to use softmax cross-entropy loss for consistency and ease of comparison. One important hyperparameter for the Fourier head is the number of frequencies. We provide a guiding principle to help choose this parameter, as more frequencies generally enhance expressive power but can lead to less smooth distributions and increase model complexity. We also incorporate a regularization term in the loss function to prevent the Fourier coefficients from becoming too large during training, ensuring that the learned PDF does not overfit to noise. We find that in low-frequency scenarios, not using regularization can yield better results, while a small regularization value works well in high-frequency cases. The way we bin the data can significantly impact performance. We should only apply the Fourier head when nearby bins are similar, and we recommend a semantically meaningful ordering of bins. For quantized numerical values, a mixed precision binning strategy can be beneficial. This involves allocating more bins to dense data intervals while controlling the allocation with a hyperparameter. Finally, we discuss weight initialization for the Fourier head. We use He initialization for the linear layer, ensuring that the outputs are close to zero. We also adjust the weights and biases to achieve a uniform distribution, which helps the learning dynamics by keeping the Fourier coefficients small. Section Summary. In this section, we introduce the Fourier series classification head, which replaces traditional linear layers for token classification by using Fourier series to output a categorical distribution from input vectors. We demonstrate its effectiveness in BPM classification tasks, showing that it significantly outperforms linear heads by leveraging the continuity of the data and making strategic design choices during training, such as hyperparameter selection and regularization. Section: Smoothness, a metric for high-frequency content. In this section, we propose a smoothness metric that takes a categorical distribution, represented as a list of values, and assigns a score based on its smoothness. A score of 0 indicates the smoothest distribution, while higher scores indicate less smoothness. We define smooth as having minimal high-frequency information. For instance, a uniform distribution has no high-frequency content and receives a score of 0, whereas a distribution derived from a sine function with many oscillations has significant high-frequency content and scores higher than 0. We aim to create a metric that measures smoothness based on a heuristic approach. Initially, we develop this metric for a general function and then adapt it for discrete categorical distributions. We use weights that sum to 1 and a measure of discrepancy, like the L2 norm. The smoothness of a function is defined by how different it is from its Gaussian smoothed version. Essentially, a function is considered smooth if it remains relatively unchanged when high-frequency content is filtered out. For categorical distributions, we define the smoothness metric specifically. Given a categorical distribution where all values are non-negative and sum to 1, we use a discrete Gaussian kernel and specific weights to calculate the smoothness score. We provide additional experiments in the appendix to support our choice of this smoothness metric. Next, we introduce a theorem that examines how the quality of the Fourier head changes as the number of frequencies increases. This is known as the Fourier head scaling law, which highlights the balance between modeling capacity and smoothness. While more frequencies allow for modeling a wider range of functions, they also reduce smoothness. This aligns with our smoothness metric, which identifies distributions as less smooth when they contain more high-frequency information. We also present a toy example where we learn a conditional distribution based on a sequence of numbers. We create 3 synthetic datasets, each containing quantized triples, where the third number is conditioned on the first 2. The Gaussian dataset is simple, while the GMM datasets are more complex. Our task is to predict the conditional distribution of the third number given the first 2. We use a multi-layer perceptron model for this task, with specific architecture details provided. We evaluate our models using 3 metrics: the average KL divergence, mean squared error, and smoothness. The results for the best performing models are summarized, and we include visualizations of the learned distributions compared to the true densities. Our findings support the Fourier head scaling law, showing that as frequency increases, smoothness decreases, but model performance improves until it levels off. Notably, the Fourier head consistently outperforms the linear baseline across all metrics. Section Summary. In this section, we propose a smoothness metric for categorical distributions that quantifies how much high-frequency information is present, with a score of 0 indicating maximum smoothness. We also introduce a Fourier head scaling law that reveals a trade-off between modeling capacity and smoothness as the number of frequencies increases, demonstrating that while more frequencies enhance modeling, they also reduce smoothness. Section: Large-Scale Study, Offline Reinforcement Learning. In this section, we examine the decision transformer, which approaches reinforcement learning by modeling rewards, states, and actions sequentially. We focus on its performance in the Sequest game from the Atari benchmark. This game features 18 actions, including moving in various directions and shooting, with 2 groups of actions that are closely related. In the original architecture, a decoder-only language model processes the context and outputs a distribution over the 18 actions through a linear layer. We modify this by replacing the linear classification head with a Fourier head. This change is intended to suggest that similar actions, like move left and move up left, should have comparable probabilities. Our findings indicate that the Fourier head yields up to a 46% improvement in returns compared to the linear head, while using the same training settings. For our dataset, we utilize the one from the original decision transformer, which includes 500,000 transitions from an online deep Q network agent trained on Sequest. In this game, the agent controls a submarine to evade enemies, shoot at them, and rescue divers, with the same 18 actions available. We employ the GPT-1 model to encode the context auto-regressively, passing it through a linear layer with 18 dimensions. The model aims to minimize the cross-entropy loss between the predicted actions and the actual actions from the dataset, which we refer to as the linear baseline. To create our Fourier N version, we substitute the linear head with a Fourier head that has n frequencies and a Fourier regularization parameter of 10 to the power of -6. We explore frequencies ranging from 2 to 32. For model evaluation, we present average reward totals from 4 different seeds. Our results show that normalized returns can be over 46% higher with sufficiently large frequencies. Additionally, as we increase the number of frequencies, the returns improve, and the learned probability mass functions become less smooth, aligning with our theoretical expectations. Qualitatively, we observe that the probability mass functions learned by the Fourier head are indeed smoother.